Welcome, SupplySide Network 365 community. I hope everyone's doing well today. I'm Jessica Urbino. I'm an Executive Director of Content with Informa Health and Nutrition. I'm very excited about today's session sponsored by Innophos. Today, you'll be hearing about why Chelamax Chelated Minerals demonstrate higher absorption. One of the things I love about this session is that you'll be seeing some new research, new studies. I love how Innophos continues to advance research on chelation and its distinct benefits. You may have caught a webinar several months ago, so everything here today will be hot off the presses, so new science. In this webinar, Dr. Bob Finn, who I'll share a little bit more about in just a moment, will present results from new in vitro digestion studies, which show significantly higher absorption of Chelamax zinc versus traditional zinc sources. Dr. Bob Finn is the Director of Research, Development, and Nutrition at Innophos, Inc. He has 20 years experience developing new products in the nutrition, food, and industrial markets. During his time at Innophos, he has authored several patents and has over 40 scientific publications. Bob and his team develop new products for key markets, including ingredients for food, industrial additives, and nutritional supplements. The laboratory is based at the Innophos headquarters in Cranbury, New Jersey. So I want to thank everyone for taking some time out of your day and remind you that we will be taking questions at the end of this session today. So please do submit your questions in the right-hand box on your screen. And there's also a chat section there. So we love hearing where you're tuning in from, what you hope to get out of the session today. And of course, just keep those questions coming. So with that, I am going to turn it over to you, Bob. Thank you so much for being here, and we look forward to the presentation.
Thank you so much, Jessica. Thank you for that lovely introduction. And thank you all for joining me today. My name is Dr. Bob Finn, and I'm the director, as Jessica said, the Director of Research, Development, and Nutrition here at Innophos. My background is in inorganic chemistry, and we've been researching and developing products with Innophos for about 20 years now. Today, I'm going to share some of our latest findings from my team on chelated minerals. As Jessica mentioned, we're investigating zinc bisglycinate in a model in vitro digestive system. So let's get started. As I said, my team has spent the last few years really focusing on chelated minerals. So I want to talk to you today in this presentation about a bit of our journey, where we began looking at understanding how a chelate is formed and how you can test it analytically. And then moving from that into how this will all work in terms of the digestive system. So I'll begin with a short overview of some of our recent publications and a description of what chelation actually is. I'll show you our data on solubility, because that's important to show how it relates to digestive conditions and bioaccessibility. And then I'll introduce you to our newest data, which is in vitro digestion data to show an improvement in absorption that comes from chelation as well. I'll finish up by explaining our three-step verification process on chelated minerals. We'll talk about the uses and benefits of chelation, and then I'll leave some time at the end for questions and answers. Innophos is committed to supplying the dietary supplement market with the highest performing minerals in the industry. Part of that commitment includes sharing evidence of the superior performance of verified chelated minerals. In the first of our series of white papers, we explained how to confirm chelation with our three-step verification process. Chelation isn't as straightforward as you would think, and there's a lot of confusion in the market, and I'll touch on that a little bit toward the end of the presentation. After we did that, we then demonstrated the key advantage of chelation, which is an enhancement of solubility through chelation, which provides protection in the digestive tract. Again, that's critical for bioaccessibility. Today, I will share our in vitro results, which build on that bioaccessibility, and start to talk about how that works in a true digestive model so that we can show absorption and suggest how that might relate to bioavailability. We are continuing our research all the time, and we look forward to sharing more results with you in the future. The The key messages of today's presentation are around zinc bisglycinate. It's 10 times more bioaccessible in the stomach and 5 times more bioaccessible in intestinal conditions than zinc oxide. That intestinal difference is really key because that's where minerals are absorbed in your body. Chelamax zinc bisglycinate has an absorption rate that's 10 times greater than zinc oxide. This again was data that we developed through our in vitro model. This data from our digestion model suggests the superior bioavailability of Chelamax zinc bisglycinate over zinc oxide. So when we're talking about mineral supplements, if you look at the overall market, it continues to grow. It's very high in popularity with a 7% global CAGR, and it's driven by consumers who have a desire to enhance their health and wellness. These consumers are learning more about these products, and they're realizing that not all mineral forms are alike. They're looking for high performance, effective supplements with specific benefits. That's where chelation comes in. So when I say chelated mineral, what exactly does that mean? What is chelation? Quite simply, a chelated mineral or a chelated compound is formed when a ligand bonds to that center in 2 positions, so it can form a ring structure. So if we work through the slide from left to right, you can see we have an inorganic mineral, zinc oxide, displayed here as a blue dot. We react that with ligands, in this case glycine, displayed as the green semicircles, and you can see the structure below to show both the glycine structures. What it does is it forms kind of a protective shell around that zinc center. What's happening is both the hydroxide group and the amino group on the zinc. Because you have 2 bonding points, you create a circular ring. This 5-membered ring is very common to see in organic chemistry. 5- and 6-membered rings are very, very common. They're very stable structures, and it's that stability that leads to the advantage of chelation in digestion. Once the zinc has been chelated, it's stable, so it won't undergo any other undesirable reactions in the digestive tract. You start with just taking zinc oxide as a mineral, it's available for reaction, and you will have these reactions occur in the stomach and the small intestine, which will hinder the solubility of the mineral. Fully reacted minerals are the key to digestion and chelation. If the reaction is incomplete, that portion of the mineral that's not protected will struggle to be absorbable later in digestion. Chelation matters. It's important because the advantage of chelation is consistent solubility throughout the digestive tract. That's critical for bioaccessibility and mineral absorption. When I talk about bioaccessibility, I'm talking about how much of that mineral is soluble in the digestive tract so it's able to be absorbed by the body. There are many factors as to why it gets absorbed or doesn't get absorbed, but it needs to be soluble to start with to be bioaccessible. So we began our studies with demonstrating the stability at the bench and moved on from there into digestive model testing. One second. We wanted to start with the link between solubility and bioaccessibility. So we started with bench reactions to understand the solubility of the minerals in simulated biological conditions. So our first test was quite simply, what is the solubility of zinc bisglycinate and zinc oxide in water? That's the data on the left side of the chart. And what you can see is that the Chelamax zinc bisglycinate is soluble while the zinc oxide is insoluble. That's not unexpected. We wouldn't expect zinc oxide to be soluble in just water. As you move to the middle of the graph, you can see we reacted both, or we tested both solubilities in a gastric condition. We created a pH 1.2 solution, and then we retested the solubility. Zinc oxide here goes from insoluble to slightly soluble at a level of around 3.1%. Why does that occur? Well, the zinc oxide actually reacts in the stomach and breaks down. It forms free zinc ions. Those are highly reactive compounds They're anion charged, or a cation charge +2, and they're able to react with other elements that are floating around in the stomach at that time. The zinc bisglycinate remains in a highly soluble state, but is still in a highly stable form. It's still formed as a chelate. So when we move into the intestinal conditions, the data all the way to the right, what you can see is we're back to a more neutral pH. The pH is about 6.8 in the small intestine. That is where the body absorbs minerals. So that's where you want the highest level of solubility. You want the highest level of bioaccessibility so that you have the best chance of absorbing these supplements that you've taken. But if you look at the zinc oxide, what happened here? It went from 3% down to 0.5%. Why did that occur? It has to do with this reactivity under these different pH conditions. Your zinc oxide is now zinc ions. And those zinc ions, when they reach the neutral pH of the small intestine, what they're actually doing here is they're able to form hydroxides that are insoluble. They form an insoluble compound and it's expelled as waste. Whereas the zinc bisglycinate, if you compare the gastric solubility to the intestinal solubility, you can see they're very similar. They're exactly the same. So you can see that protection that you get from having a chelated mineral. It's protected and it stays soluble and stable through both the stomach and the intestinal tract. Like I said, the intestine is where these compounds will be absorbed. So zinc bisglycinate is much more soluble under these conditions, even when we mimic the intestinal conditions, whereas zinc oxide is not. So let me look at this data with you in a different way. I'll overlay the data on this pictogram of a digestive tract. So if we start with zinc oxide, if you're to take a zinc oxide tablet, it reaches your stomach, you have moderate solubility of 3%. That 3% solubility comes down into the small intestine where your body would look to absorb the zinc and the solubility drops to 0.5%. What happens? That material is expelled as waste. It's a solid material now and it's no longer bioaccessible. If we compare this to zinc glycinate, we have a good solubility in the stomach. We have a good solubility that maintains in the small intestine. So why is that important? That compound has remained intact, stable, and bioaccessible. The oxide, on the other hand, gets precipitated and is no longer available for absorption. So you can see in the little graphic that that tablet of zinc bisglycinate is able to be absorbed in the small intestine where your body needs it the most. What's the value of taking a supplement if the body cannot absorb it? So that's all well and good, but these are all bench tests. We're just testing these solutions at different pH conditions and learning what we can. The next obvious step here is to move into an in vitro model. The purpose of an in vitro model is to simulate real digestive conditions outside of a life form. So we're trying to do this at a bench scale with simulated solutions so that we can understand what would actually happen if we were to take the tablets, if we were to have a human clinical trial or something similar. So what do we start with? We start with a dissolution vessel, and in that dissolution vessel, we have simulated gastric fluid, the fluids that you would find in the stomach, or at least the pH range that you would find in the stomach. We add in our tablets, both a zinc oxide tablet in one reaction, zinc glycinate tablet in another, and we normalize the zinc level to make sure that we're having the same amount of zinc that can be soluble throughout the experiment. We allow that to stir for the time of digestion in the stomach, so for 20 minutes. And then after 20 minutes, we raise the pH to match the small intestinal conditions. We use a simulated intestinal fluid, and once those conditions are reached, we add in these permeation chambers. Permeation chambers are critical here because they have a coating that I'll blow it up here so you can see it a little better. It's a monolayer of Keiko-2 cells. These are human intestinal lining Keiko-2 cells. So this is the cells that are in the small intestine. This is the area where your body actually absorbs the minerals. So we add in the human Keiko-2 cells in these permeation chambers, and we wait to see how much of the zinc actually gets absorbed by pulling samples at a time basis in both the dissolution vessel and the permeation chambers. This creates a simulated digestive system as close as it can be in an in vitro environment. So what happens? The zinc bisglycinate actually is able to pass through the CaCO2 cells. You can see them kind of looking like stacked Tic Tacs. That's what one of my colleagues said yesterday, but the amber layer there is representing the CaCO2 cells. The zinc bisglycinate is able to pass through. It stays in that stable form. It's highly soluble, highly stable, and it passes through the CaCO2 cells. The zinc oxide, actually, the digestive system itself is working against zinc oxide. By the time you've reached the small intestine, zinc oxide is precipitated back to zinc hydroxide. It's not bioaccessible. And so as we see, there's very little absorption through the CaCO2 cells. So I'll get into the data here in the next couple of slides so you can see it more clearly. This is the results from the dissolution chamber. So this is the overall chamber tested throughout the experiment. This is 20 minutes of conditions for the stomach and then 120 minutes of conditions for the small intestine. And what you can see when you look at the graph is the green line is our zinc bisglycinate. This is our chelated mineral. It's immediately soluble. It reaches, about 45%. The total dosage is immediately soluble, and then levels off at about 40%. So a nice steady climb of high soluble zinc glycinate from the dosage that we provided into the dissolution chamber. Whereas the zinc oxide never really gets there. The solubility is low to start with, and as we continue to move forward in time, it barely gets above 10, but it really stays at around 8% soluble for the duration of the experiment. So if you look at the difference in the solubility in those last two data points, we're 5 times more bioaccessible when it matters, 5 times more bioaccessible in the small intestine, and that's where absorption occurs. It's a huge difference. Here's the really critical data though. This is the data that we collected through the CaCO2 cells. So this is after the zinc has permeated those CaCO2 cells and has been in those permeation ports, we've sampled from there as well. And what you can see is, again, a steady increase of zinc bisglycinate reaching a higher level of solubility, a higher level of absorption. Zinc oxide falling short through the entire experiment. Ultimately, at the end of the 140 minutes, we were 10 times more soluble, 10 times more absorbed through the CaCO2 cells than the zinc oxide. This is exactly what would occur in the body. It's just simulated in this in vitro model. The zinc from the chelated source, much more absorbable. That absorption suggests that it would be equally more bioavailable. The in vitro model results suggest that chelated zinc bisglycinate will be more bioavailable than zinc oxide. That demonstrates the performance and the value of chelation. So now that you understand why chelation is important, how do you know when you're buying a chelated mineral? I did some research and I pulled some supplement fact panels from just 3 random supplements that you can find online. And what you can see from these is the product labels, they can be confusing or even misleading to customers depending on how the minerals are labeled. If you look at fact panel A, the magnesium source comes from magnesium glycinate chelate and magnesium oxide. Many times this is done in order to boost the overall magnesium level, but we now know the magnesium oxide is less likely to be absorbed. So what this is really giving you is a blend where one is chelated, one is not, but overall, you're not getting the full value of 200 milligrams of chelated magnesium in that case. If we look at the supplement fact panel for B, what you can see here is the zinc is shown as zinc gluconate. The zinc gluconate comes from 385 milligrams of chelated zinc gluconate, and that leads to 50 milligrams of zinc. That makes sense for a fully chelated compound. That's the amount of zinc you would expect. So in that case, I would expect that we would have a fully chelated mineral. Supplement fact panel C shows magnesium from magnesium oxide, comma, amino acid chelate. What does that really mean? Well, I don't really know. It's probably a blend. There might have been a reaction. There might have been some sort of partial reaction. But you can see, again, we're talking about 250 milligrams in the dosage for magnesium. And so that tends to lead me to believe that there's a lot of unreacted magnesium oxide there. So how do you know what you're buying? Are all these similar? Are all of them high performing? No, they're not all high performing. These high concentrations are meant to boost a daily value, but they don't equal quality. They're not the sort of quality you would get from having chelation present. So it doesn't always matter whether the value is 200 milligrams. If it's going to be an oxide or a salt, it's less bioaccessible and less absorbable. So let me talk to you a little bit now about how we've moved on with testing. At Innophos, we wanted to lead the way in both test methods and provide transparency to the industry. As you can see to the right, we have an FTIR on the screen here. Most companies are very familiar with the method. They understand it as an identification method. But alone, it falls short to prove chelation. This data is fine to show lot-to-lot uniformity, but what it doesn't show is the position of the bonds. It doesn't show that ring structure forming like I talked about a few slides ago. That ring structure is the key to chelation. We want to see the zinc bound to an oxygen and the zinc bound to a nitrogen to show that structure. So at Innophos, we embarked on building a stronger test methodology. We started with X-ray diffraction. In X-ray diffraction, it's a method that can actually determine the position of the atoms of the structure. So while that spectrum at the bottom of the screen, if you're not familiar with XRD, might look very similar to the FTIR, what that data is actually telling us is exactly where the zinc is and exactly where the glycine is. We can see how close they are. We can see the bond lengths, the bond angles, the entire structure. So at the end of running the X-ray diffraction, we get this. We get an actual picture of the compound. This is our zinc bisglycinate, and you can see that there are two chelated minerals forming those ring structures that I've been talking about. That's our actual data. That's not something that came from a drawing program. We also added TGA, thermogravimetric analysis. The reason we added TGA is TGA can show us the decomposition temperature of the ligands. If the ligand is bound versus unbound, those decomposition temperatures change. And so we can tell the purity of the compound simply by running TGA. We continue to run FTIR because it is a valuable tool for lot-to-lot uniformity. And as we put all three together, we have our three-step verification process to prove full chelation. Step one is X-ray diffraction. That confirms our structure. Step two is thermogravimetric analysis. That confirms our purity. Step three is FTIR, and that confirms our consistency. All three together provide us with the best and most thorough testing process in the industry. And our Chelamax brand is all tested against this three-step verification process. So now that I've talked to you about the value of chelation, what is chelation, and how we test for chelation, how do you use something like this in an actual formulation? Let's get into some of the uses and benefits here. Most people think about, when you're talking about formulations, many people think traditionally capsules and tablets, but formulators today are challenged to add supplements to an ever-expanding list of dosage forms. You look at the density data here, zinc bisglycinate is actually favorable versus zinc oxide. It's got a higher density, you can fit more in a capsule or a tablet. Particle size is similar, it's slightly more coarse, so you get a better flowing product. But where zinc bisglycinate really stands out is the solubility. Because we come in here with a higher solubility, a product that's not insoluble, we open ourselves up to all of the liquid dosage application forms. That includes soft gels, liquid applications, but it also includes gummies. Anything that you want to have, translucent, semi-transparent. You can't have products precipitating in, they'll look like speckles or spots. That's where chelation can really be an advantage as more and more of these applications and dosages are moving to a liquid form. So this provides value for both manufacturers and consumers. On the manufacturing side, we've got a great product with solubility and stability. We've got great dissolution rates, and we offer a variety of particle sizes, concentrations, and low impurities. On the consumer side, consumers are looking for efficacy. They're looking for high-performing minerals. We're providing the data here to show that Chelamax has that high performance. We have increased bioaccessibility, we have improved absorption, which suggests bioavailability, and we have a high level of confidence in both our product and our efficacy, because both of our internal analytical testing and now the data we're getting to support it in vitro studies. So to summarize, we have the data to support enhanced solubility and superior absorption. And that superior absorption suggests bioavailability. We have our own unique 3-step verification process. It's the best in the industry, and it proves our quality and our efficacy. We have the expertise in tableting and the application support to help people formulate as they work through the new formulations that are now available to them with a highly soluble chelated mineral. The Chelamax brand stands for proven, science-backed efficacy and quality. Our Chelamax minerals include magnesium, zinc, calcium, chromium, and vanadium. Chelation matters. At Innophos, we've invested in the research to show the many benefits of chelates and ensuring the purity of our products. Thanks for joining me today, and I'm happy to answer any questions you may have. Thank you.
Thank you so much, Bob. Such a rich in information presentation. And I want to remind everyone, keep the questions coming. We have a few great questions. Don't be shy. Put your questions in the chat. We will answer them. And yeah, Bob, that was so great. I love how you talked about, obviously, the science behind chelation, but also your focus on transparency every step of the way, which obviously is so, so important to the process. So I want to kind of pick up on that research piece that you left off on, and I'm curious what Innophos's plan for future testing looks like, with that being such an important part of your business.
Yeah, I mean, it's really important as we develop this data. This is our in vitro testing here only included zinc, but we have other Chelamax minerals that we're interested in providing the same kind of data with. And obviously, as I sort of teased out in one of the early slides, the next step after in vitro is moving to an in vivo environment. So we're looking at both of these right now and trying to decide, what our next steps are going to be. But that's certainly the roadmap. Build out the minerals that have this kind of support, and then look to grow to the next level where we move into life forms.
Great, thank you. And here's a question. This person knows what they're talking about. The question is, what do you add in the permeation chambers midway in the experiment?
Oh, yeah, we have to add those midway because of the conditions. We're mimicking the digestive conditions to start with, and the pH is very low. So we can't add the permeation chambers too early, or the Keiko-2 cells won't survive. We have to get to the conditions of the intestine, the small intestine, before those can be lowered in so that we can make sure that they're in the conditions that they're normally under. And I should add as well that in these experiments, we actually add a negative control into the test. We add something called atenolol, which is not meant to go through Keiko-2 cells. So we're testing for that as well to make sure that there's no ruptures or breakages within the Keiko-2 cells. If we see a high concentration of atenolol, then we know something has occurred with the Keiko-2 cells, and we have to restart the experiment. So we did have that negative control in there, but I just didn't include it on the slide.
Okay, thank you for that. This is a great one, and actually probably I don't have full clarity on this for just in general in the supplement space. What is the difference between bioaccessibility and bioavailability?
Yeah, it's a key difference, true. Bioaccessibility is literally how much of that mineral is soluble in your digestive tract and available to be absorbed. Bioavailability is how much gets absorbed. So we're suggesting bioavailability because we've gone through this in vitro trial and seen the absorption through those cells. You really can't claim bioavailability until you've done the in vivo work that shows that you actually have absorption in a living form.
Very interesting. Thank you. I feel like I should have known that before today. So I'm so glad that I now know that information.
Sometimes they get used as synonyms, but they have very different meanings.
Yes, yes, absolutely. Another question, I really liked how you were talking about the higher solubilities that chelation supports, and that seemed to me really does lead to formulation innovations. I am often inspired and excited by all of the different delivery formats that we're seeing in the supplement industry. So kind of just a personal question for you, what are you most excited about seeing formulators do with chelation and chelated ingredients in their product formulations that can really meet consumer needs now?
I mean, to me, it's efficacy. You know, like anybody, before I started working on chelated minerals, when I bought a supplement, I turned it over on the back and looked for the highest percentage. But to know now that this form really leads to efficacy, it's opening the doors to a number of different formulations. Like I said, liquid formulations are a very easy, immediate fit in. And there are, with an aging population that struggles to swallow pills, that could be a really unique feature. We're seeing more in terms of, personal kind of supplement maintenance. That could be a really interesting space as that starts to develop a bit. But yeah, just people understanding that chelation is a key feature in order to get absorption for me is the most exciting piece of it. Like I said, I'm a chemist, so I want to see the stuff be used because it's effective.
Yeah, absolutely. Efficacy. I was like, yeah, gummies. We're so excited about gummies. But really, when it comes down to using innovation for the right reasons, it really is about efficacy. So I love that you emphasize that. Another question we just got in, is there a difference between chelates and glycinates?
So I use the two as synonyms today because we were talking about zinc bisglycinate, which is a fully chelated compound that Innophos offers. The reaction has to have occurred correctly for the chelation to have occurred. But I can tell you, if it's a Chelamax glycinate, regardless of the mineral, it is a fully chelated compound.
Okay, so chelates and glycinates used interchangeably today.
Yep. The glycinate is one of the amino acids that we use here. It's one of the more popular ones. It's got a lower molecular weight, so you can get higher concentration of the zinc per gram or the magnesium or whatever you're using because of the low molecular weight of the glycinate.
Okay, great. Thank you. And thanks for that question. One last call for additional questions. And yeah, Bob, before we wrap up, if we don't get any other audience questions, I'm guessing we have a lot of formulators here today. Any other bits of information that you want to share with them, and how can people reach out to you with questions? I know you have your contact information here, but any kind of parting words for companies that are considering chelates in their formulations?
I would just reemphasize that those earlier white papers that I started discussing in the presentation, they have more data in them. I just was kind of, just covering the little bits so that you can see the background here. So if you want to learn more, those white papers are on our website. So you can go to our website and download those. They're all there available for you.
Great, and we did get a final question in, and it doesn't have to be final, we have time, so if anyone has more, please send them. But question is, how do chelates compare to liquid ionic materials? Oh, minerals, excuse me. Liquid ionic minerals. Yeah,
so our chelates are generally sold as powders, so that they can be formulated in a number of versions. If you have an ionic mineral, you likely have a compound that is not fully reacted because it's got ion right in the title there. So you're probably looking at a material that could struggle in this sort of an in vitro test. I'm not sure how the solubility would remain. We haven't tested them directly yet.
Great, thank you. I think that is our last question. So Bob, anything else before we wrap up for the day?
That's everything for me. Thank you for your attention. Thank you, everybody, for all the great questions. And we hope to hear from you.
Yes, absolutely. And yes, thanks everyone for taking time out of your day. Thank you, Bob, for such a great presentation. And I'm sure many more connections will be made after this session, but everyone have a great day and be sure to check out the agenda and SupplySide Network 365 for all of the great programming that we have coming up. Have a great day.